Hello, everybody. We are presenting on ice screw testing. I'm Martin Noe.
I'm Carson Bruning.
I'm Alex Phillips.
In the field, ice screws are placed into naturally occurring ice from waterfalls or glaciers. Once a screw is placed, various ropes and slings can be clipped to the hanger of the screw based on the needs of the user. The primary uses for screws are for protection from falling and for building anchors. When a climber falls with their rope connected to a screw, the rope will go taut and transfer the load from the fall onto the hanger of the screw. The equipment company Petzl has performed tests of loads under various fall scenarios and documented loads from 4 to 6 kilonewton, depending on the nature of the fall or how the belayer reacts. Ideally, all ice screws used for fall protection would be able to reliably withstand loads greater than 5 kilonewton. Tests with longer ice screws have been done using load frames by affixing an ice block and pulling onto the screw to simulate a load in the field. Testing of longer screws showed that both the ice and the screw itself can fail under high loads that exceed 5 kilonewton. With shorter screws, it is believed that the ice will fail before the metal components of the screw yield from bending stress. Currently, there is no testing data published for any ice screws shorter than 10 centimeters. According to threads on the climbing discussion forum Mountain Project, there was a lot of interest for people to test 7 centimeter screws in a load frame, as the climbing community hopes to better understand the appropriate usage of short ice screws. Performing research and corresponding with members of the climbing community synthesized the key question, which is how much pull force can a short ice screw hold before failure? The objective of this project is to quantify the strength of short ice screws under tension loads to improve the safety of recreational and professional climbers. On the bottom right, you can see the 5 screws that were used in this test. And on the top right, you can see a range of longer screws down to shorter screws.
So, a little bit about our test plan. To create realistic conditions in the lab, a custom load frame fixture was manufactured to fix ice blocks inside the load frame. The ice was uniformly frozen in plastic trays using tap water to create a consistently strong medium to place the ice screws in. The metal load frame fixture was chilled in the freezer before each round of tests and then bolted to the load frame. Ice was removed from the trays and placed inside the load frame fixture and secured by shims and bolts. It is important to note that lab conditions involve consistent ice density, rate of loading, and rate of loading, which are not all the same in the field. This test was performed using a static load with a load rate of 1 kilonewton per minute, which differs from outdoor scenarios in which the force is dynamically loaded when the climber falls. The goal of this experiment was to control the temperature, ice quality, rate of load, and ice screw placement so that the screw length was the only variable changing between trials. This was intended to provide consistent data to help observe trends in strength across the 6 to 8.2 centimeter screws. In the bottom right, you could see a schedule of our project throughout the semester and the different steps we took along the way.
The majority of our measurements came from digital tools used in the lab. Load forces were measured via the load cell sensors in the Instron 5900R load frame, which measures values in newtons to the 100th decimal place. Temperature of the ice was recorded via a handheld infrared thermometer, which was placed directly in front of the ice face where the screw was placed. The mass of each ice block was taken in grams on a small digital scale. The dimensions of the shattered ice cone, if present, were measured with a pair of digital calipers. Room temperature values were recorded for each test via a liquid and glass thermometer, which was set out in the lab space. And this slide is a visual of the equipment that we used and the parts that we used. Some of our parts incurred some costs, include the load frame fixture steel and the ice trays that were purchased to freeze our ice blocks.
The procedure for the experiment that we performed was the same for every single trial, which started with removing the load frame fixture from the freezer and affixing it to the load frame base, attaching the plastic catch tray below the metal fixture, feeding into a large bucket to keep the load frame dry, attaching sling and carabiner to the upper pin, and setting out ice blocks to allow them to warm up to about -10 Celsius. While they're warming up, we chiseled off any obstructions to flatten the ice face. After that, we removed the ice blocks from the ice trays and took pictures of the faces and the sides and recorded the mass of each block. When the blocks reached -10 Celsius, we inserted a singular block into the load frame fixture and used shims and also bolts on the side to secure the block in place. We then inserted an ice screw fully into the center of the ice face and attached a carabiner to the metal screw loop. We jogged the load frame to get rid of any extra slack in the sling, and then affixed the camera in front of the load frame and also hung the plexiglass shield on the metal brackets above. Before initializing the test, we took a photo and then ran the test using the Blue Hill software. Afterward, we stopped the test when the screws blew out of the ice, which was automatically stopped by the Blue Hill software with a 50% force reduction parameter. We then observed and documented the ice after breaking and recorded the dimensions of the break. We then removed the broken ice and cleared the work surface and also saved the data into the testing folder. And then we were ready to repeat the process.
So a little bit about our risk assessment. We had some risk and hazards with this experiment. One of them was ice and metal debris flying into the air and water posing a slipping and electrical hazard during the test procedure. To mitigate this, we used a plexiglass shield to block the ice. And then after each test, we would sweep up any debris or water. And we would also continuously wipe down surfaces to be dry and conduct the experiments away from any electrical sources. On the right, you could see a little image of what it looked like.
So here are the results from our experiments. Table 5 shows the load at which the ice screw failed for each trial. For this data, average max load and standard deviation for each screw length were calculated. These average values can be seen below in Table 4.
So some more graphics from our data. The trend line in Figure 5 shows the maximum load increases as screw length increases, meaning that longer screws are stronger. And then in Table 3 in the bottom left, you could see the ambient measurements that were basically constant across all our tests.
So some analysis of our results. The highest load value from the set of trials was approximately 5.7 kilonewton, but most of the trials averaged around 3 to 4 kilonewtons, which was consistently lower than the desired 5 kilonewton strength rating. More trials were performed for the 7 centimeter ice screw to gauge the repeatability of the testing methods. Based on the standard deviation of the 7 centimeter trials being greater than 1 kilonewton, the test is not very repeatable. Analysis of the temperature versus max load data indicated no correlation between ice temperature and pull strength. However, in the lab, there were visible differences in ice characteristics. Ice at negative 25 Celsius was far more brittle and would often experience thermal shock, which is a phenomenon in which the ice would start cracking when it was exposed to rapid warming. The brittle ice was also more fragile when inserting ice screws, and in some of these instances, the ice block completely failed during setup. As testing progressed, the target temperature for ice blocks was achieved at negative 10 to negative 5 degrees Celsius. In order to validate testing methods, trial 16 was performed with a 13 centimeter ice screw rated for 10 kilonewtons. The test was aborted at 8.3 kilonewton when the screw was still holding, but the hanger was beginning to bend. This indicated that the ice could hold screws at higher loads than the short screws were capable of withstanding.
So there was a significant amount of variability within the tests, which affected the consistency of the results. Certain blocks had pre-existing abnormalities caused by the freezing process or thermal shock, which resulted in cracking when the blocks were loaded into the fixture. As a result, the ice often failed in an unrealistic manner, experiencing cracking that compromised the entire block rather than the ice around the screw fracturing in a cone shape. Conical fracturing is a characteristic of rear-world screw failure because screws are placed in large ice features that are not compromised when the ice around the screw fails. Trial number 1 was the only test that achieved cone-shaped ice failure. In this trial, the ice around the screw shattered explosively at a load of 5.7 kilonewtons, but the ice block remained intact. While this result was not repeated in further trials, it indicates that short ice screws have the potential to hold larger loads than the averages from this set of tests if placed into larger ice features. The variability of our experiment, plus the low number of trials for most screws, resulted in a very high standard deviation within the data. The standard deviation would likely be decreased if the conditions of the test setup were improved to reduce ice variability and more realistically simulate waterfall ice conditions.
So in summary, the pull tests performed on the 6 to 8.2 centimeter ice screws were inconclusive due to high uncertainty and therefore do not accurately represent the strength of the ice screws. The highest load seen across all trials was approximately 5.7 kilonewtons, but the majority of trials averaged between 3 and 4 kilonewtons. Based on the loads that the screws failed under, they did not meet the standards of an average fall. It is possible that trial number 1 is a more accurate representation of short ice screws because the ice failed with the realistic cone fracture instead of compromising the entire ice block. And trial number 1 was the 5.7 kilonewton trial. This indicates that short ice screws may be capable of holding loads closer to 5 kilonewtons and therefore may be able to withstand forces generated from an average fall.
We learned a lot from this experimental process, and we have a lot of ideas for future tests. So manufacturing more load frame fixtures would allow freezing the ice directly into the fixture. Freezing the ice into the fixture may prevent the ice block from being compromised, which would yield better results. And again, compromised meaning that the whole block fractures apart. Another recommendation is to run the experiment at more temperature intervals to see what temperature the ice screw will hold the greatest force. Also, building one fixture that's approximately twice the size of the current fixture would allow for 2 equalized ice screws to be tested, which is a configuration commonly used with shorter screws as it reduces the force on each screw. Another future test would be to take short screws into the field and set up drop tests using real waterfall ice to closely match realistic scenarios. Here are the references for our presentation. Thank you for listening.